told y'all at the beginning of the semester that I'm going to present at a conference in Las Vegas. And so I'm going to be gone. And I know it's just unfortunate. We had a holiday. We had Elsa decided to move into Acadiana. We had the snow days, but that's life. And this is a hybrid class. Although I prefer to meet in person, we got to do what we got to do. So all of your lectures for Unit 1 are there from my fall semester. So in other words, you have access to all the things. So I'm going to be gone Wednesday, Friday, and Monday. Wednesday to Wednesday. So I'm going to be missing 4 classes. The lectures are already posted. They're already there. Today I'm going to hit up some basics of trigonometry. I'm telling you, I promise you, it's going to make sense once we apply it to stuff we know. But Lindsay is going to be available. So in other words, although we won't have in-person class, Lindsay is going to be available before, like, till 8:20. You could go over. Lindsay will be available until she has to go to physics, specifically for people that want to review the 310 stuff. Let's talk about illusions. Let's remind ourselves about muscles, contractions. Guys, when we get into specific muscles, this class is about you applying knowledge, because in your internship, your world, you got to be able to play. You got to be able to apply. And like I always say, if I memorized every rule of basketball, it doesn't make me a basketball player. I can't get better unless I play. Because it's only when I'm playing and I assume everybody's right-handed and a left-hander goes by and I'm like, oh gosh, we got some left-handers. You don't learn that in a book. You got to play. So when we get into these specific muscles and I'm teaching you how they pull in certain directions, the contractions, the motion, all that stuff, I'm assuming y'all been playing so that we could play. Okay? So that is your kind of dual assignment. You'll watch lectures for the next week online, but Lindsay will be available for you to practice the 310 stuff. So that way, when we get into the muscles of the cervical vertebra, which is on your first test, you're going to have 4 major muscles. I'm just talking about the all-stars, the prime movers. You're going to have a right and left sternocleidomastoids that pull in certain directions of motion. You have right and left erector spinae. But I won't have time to go over all the motion. This is right lateral, this is left lateral. This is right lateral, this is left lateral. This is extension. Remember all those illusion stuff? That's why we got to practice that stuff now. So Lindsay will be available. What'd you say you have, the me group? What's that fancy stuff?
But it's a 310 group.
But that's okay. If you want to practice the 310 stuff, so in other words, you can still join the 310 group me. She'll be available in the lab certain times if you want to practice. I strongly encourage you to go back through 310, specifically motion, agonistic groups. Guys, you know what I'm doing? We have cervical flexors and cervical extensors. All I'm going to say is who are the cervical flexors? And I'm going to teach you how those muscles pull in certain directions of motion. Who are the right lateral benders? Who are the left lateral benders? Who are the? But remembering the concepts of agonists and how they pull in specific directions of motion, those illusions of motion, muscles influence motion through contraction. Remember that? Because that's what most of our students, and it's not just you guys, it's professionals too. We struggle with contractions because it's nuanced in context and it depends. Remember, we don't say if I see extension, it has to be because of this muscle, right? Because I could have extension because of bicep. And I could have extension because of tricep. I could have flexion because of tricep. We can't just say this motion, this muscle. And so that was all 310, using the clues to identify the agonist, then observing the motion, and then saying, well, if these muscles do this motion, it has to be through this contraction. We will not have time for me to teach you all that stuff again. So that's why Lindsay's here, to help play, help practice, so we can get back into game shape so that we can apply it to specific muscles of the body, okay? Anything you want to add, Lindsay?
I'll be here Monday and Wednesday after physics. In the mornings, 7:30 a.m.
Absolutely. So again, videos, lectures are already posted. So I don't have to, I'm not going to email you and say Monday's lecture. They're all there. Lindsay will be here as a supplement to help you with 310 stuff. And your first unit is all the physics that we're going to need just for class. And all the physics I'm teaching you is going to apply to the muscles. Muscles, motion, contraction. No wasted stuff. And then we're gonna have one joint for the body. I'm gonna give you the cervical so that I can teach you how to play this cross-sectional anatomy game. Which, true story, I was MC in a fundraiser this weekend, and one of my former students, who's a doctor of chiropractic, was there with her husband, who's also a doctor of chiropractic. I hadn't seen her in 10 years. And she came over and she said, I can't tell you how useful your cross-sectional approach to anatomy was in graduate school. We keep things simple. And so that's a tool we're going to learn for the muscles. All right. Thank you, Lindsay. All right, guys. Any questions before I get into the trigonometry? Okay. All right. I know trigonometry. I get it. But I'm hoping that I pitch it or spin it in a way that you've never had it pitched or spin before, and you're like, oh, that's what those things mean. First of all, we know remember from our planes and axes lecture, sagittal, frontal, transverse, what did you notice about those three planes? Weren't they all perpendicular to each other? They're all in right angles, right? They were all in right angles to each other. That's kind of neat. What do we also know about our Cartesian plane? You guys, the Moodle notes are posted. You could pull it up if you want. Basic biomechanics trig. And so you can follow, if you're watching from home, you could follow on your computer. And I'm going to use my board and talk and tell stories. That's how I teach. What do we also know about the Cartesian plane? X and Y are at right. Ground and gravity are at right angles. Here's the X, here's the Y. Unfortunately, a chalkboard is only kind of a two-dimensional viewing space. There's no third dimension. That's why when you go to a 3D movie, you get the special glasses and it comes with depth. So our third dimension is our Z-axis. That'll be coming at you. Muscles can pull in three dimensions. Is the reason I'm bringing it up. You're going to have certain muscles that pull sagittally, frontally, and transversely. But they're all right angles to each other. They're all at 90 degrees from each other. The way I like to keep things simple. If the X is an apple and the Y is an orange, they're related, but they're not the same. Don't compare apples to oranges. But you know what we can do? If X is apples and Y is oranges and Z is banana, the real world in terms of human motion, we don't live in a robot world, is a mix of all that stuff that we call fruit salad. So there's apples, there's bananas, and there's oranges, but it's all mixed together. What I mean by that is, yeah, it's nice to have X and Y. Let me get my lightsaber because I think the effects are better. But in reality, it's super hard for me to take a softball and throw it perfectly in the Y. It might drift a little. It may drift back. It's super hard. Anybody ever done a vertical jump and you're trying to jump as high as you can, but if you drift even 3 inches forward, that means you didn't put all your energy into the Y. You gave a little bit into the X. There was a little bit of fruit salad. So the reality is that it is really hard to have forces in motion perfectly here, perfectly there, perfectly here, perfectly there. Most of the time, it's in some combination. Does that make sense? In other words, it's a combination of X and Y. It's a combination of Y and X. It's a combination of X, Y, and Z. That's how the real world works. We also know that only Y forces, up-down forces, can move things in the up-down. I can't push something across and make that force make something go up. X forces influence X motion. Y forces influence Y motion. Z forces influence Z motion. So I just established that the rules of physics say everything has to be in its lane. But in the real world, it's bumper cars moving all over the place. So how do we make sense of it? Trigonometry. What trigonometry does, who balances their checkbooks? Anybody balance their checkbooks? I don't. My wife it's one of the many great things she does. I have no idea about money coming in, money coming out. But doesn't it make sense if you're working, let's say you're doing a fundraiser, you're working, and there's a lot of transactions happening, you need a way to say what's yours, what's mine, if it's all clumped together. So that's what trigonometry does. We might take a baseball and throw it from the outfield and measure its velocity, its magnitude, and for me, something slow, like 50 miles an hour at my age. But if I throw it here, some of that motion is going up and some of that motion is going across. It's like our money is combined. So what we have to have is a mechanism to say how much of that motion is up and how much of that motion is across. Or if we were measuring force, there's fancy force plates and other tensiometers that we can measure force. So if I'm pulling on something and it's at an angle, well, some of that pull is X and some of that pull is Y. And only the X can influence X motion and only the Y can influence Y motion. So if it's in a combination, I have to have a way to separate the X from the X and the Y from the Y so that I can balance my checkbooks in each direction. Does that make sense? X forces influence X motion, Y forces influence Y motion. So when we have a resultant that's somewhere in the middle, I have to have a mechanism to say how much of it was here and how much of it was there. Does that make sense? That's what trigonometry is. In addition, the elegance and the beauty is a lot more simple than what I think most of us that have had trigonometry is. This is my 2 cents. All trigonometry is, guys, is the relationship between a magnitude, a resultant, whatever it is, distance, velocity, force, and the angle that it's being applied, and the components to the different sides that make it up. What do I mean by that? Let's pretend this is a 10-foot basketball goal that we're going to put up for our kiddos to play on. Let's say it's in the schoolyard and we're putting it up as a project for an elementary school. When the basketball goal is laying down and it's from base to rim, it's 10 feet, but it's not 10 feet tall. It's 10 feet long across in the X. It has 0 height. Trigonometry is if I raise the goal 20 degrees from the ground, well, now I increased its height and I decreased its length because it's impossible to do so. And if I increase the angle even more, let's say 45, I shortened it in the X and I raised it more in the Y. And if I raise it even more, it's getting taller and taller and taller as it's getting shorter and shorter and shorter until all of it is in the Y and none of it is in the X. Guys, that's all trigonometry is. And it works because these things are at right angles to each other. So now let's do velocity. I throw a baseball I don't, but let's say 100 miles an hour, a nice even number. If I throw it all in the positive X, none of that motion was up or down. It was all here. But if I angle it and I throw it 100 miles an hour, let's say I'm shooting a projectile, well, some of that motion is here and some of that motion is there. Common sense question. If I launch, let's say this is a potato gun, you know what that is? You put a potato and you put some hairspray in it and right? If I take the potato gun and I shoot it at 100 miles an hour and I give it a small angle, like only 10 or 20 degrees, would most of that velocity be across or up? Across. You That's trigonometry. If I take the same potato gun and I do this to 80 degrees from the horizon and I shoot it with the same velocity, is most of that motion going up or across? You know this. It's trigonometry. So how do we extract? How do we balance the checkbook? Take out your cell phones or go to your computer and give me a scientific calculator. I didn't know this, but if you unlock the rotation part of your computer and you rotate it, it'll give you all these extra options. We're looking for the infamous, the beyond famous sine, cosine, and tangent functions. That's all that is, guys. That is all that is. Okay? Guys, what is another way to put 100%, 50%, 25%? Y'all remember the trick with decimal places? Like, in other words, this is just this. This is this. And this is that. Y'all remember that? It's going to be fun. Check out this. I would like for you to put in, so I'm assuming you guys had this in high school or college. If not, no problem. But remember how we had anatomical position in 310? In mechanics, we have to have an anatomical position. So that way we know where to start. That's what positive X is. That's what from the horizon is. It's a zero. It's an anatomical position. So that way when I say 80 degrees from, 80 degrees from what? 80 degrees from here, 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 right? 80 from anywhere. Okay? So it's our anatomical position. Positive X, FTR, from the horizon, FTH. If I tell you guys that the potato gun, the potato at 100 miles an hour at an angle of 3 degrees, that's given. That's what you can measure. You can measure that. Okay? And you can have a goniometer. So here's your given. We fire a projectile at 100 miles an hour. Now, Campbell, why don't you say meters per second? Didn't suppose. Miracle. In other words, I have nothing against metric. I just don't know metric. I don't know how fast 100 meters per second is because all of our roads and all of our dials are miles an hour. I know what that is. So that's why I use it. It's nothing personal. It's just what we know. So if someone's like, so-and-so jumped 1.8 meters, I'm like, that's awesome. Conversion. Oh, it's this many feet, right? So it's just stuff we know. So that's why I'm using it. All right, given. We launch a projectile 100 miles an hour at an angle of 30 degrees from the horizon. All that means is 30 degrees from positive X. We have to have a reference. So here's the question that I just set up. We know that some of that motion is in the X and some of that motion is in the Y. Common sense says some of it is in each. All trigonometry does is allow us to extract. Give unto Caesar what is Caesar's, as Dr. George used to say. How much of that motion is X motion? How much of that motion is Y motion? Because X forces only influence X motion and Y forces only influence Y motion. It's like two different checking accounts. And you have a group project where you both make money, but eventually you got to separate what's yours and what's mine so I can do my taxes. So check this out. You guys told me, you knew this. You said that if we launch something at this shallow of an angle, most of it is going to be across. You know this. So let's check it out. I'd like for you to go to your scientific calculator, and I want you to put in 30 sine. 30 sine. Just trust me. I'll explain the whys, but just 30 sine. And tell me what you get. It should be some decimal places, right? It should be a point something. Okay, negative 0.988. Now, a lot of times, guys, disregard the negatives, because that's just direction. It's not like I owe potato gun something. But if you remember, if we have the magnitude is 100 miles an hour, our angle theta is 30 degrees from the horizon. Theta is arbitrary. I could call it alpha. I could call it whatever. It's just our angle. It's all me. Your brain knows that most of that motion is going that way. The trig, the sine, and the cosine, all that is to help us determine what percentage, this is brilliant, what percentage of that 100 miles an hour, whatever it is, what percentage is X or Y? That's all it's doing. Sine and cosine is just telling us what percent of that overall amount, whether it's a 10-foot goal or it's a 100-mile-an-hour fastball, what percentage of it is in the X or the Y? If you guys remember, the sine function is the opposite side over the hypotenuse, right? Do y'all remember that from high school? So in this case, the opposite side of 30 is my Y component. So when I say 30 sine, it's telling me that that's the percentage of this that's going up. And you know how I know that? Because this translates to that once we move the decimal place over. So what was 30 sine again? Okay. 30 sine. 0.5. So here's what we have to do, and this is what I love about this. Check your calculator. It has to be in degrees and not radians. Radians is arc distance. So the person, I got the same thing, the 0.988, the negative 0.98, but mine is set to radians. So we have to set it to degrees. Y'all, we've all made, this happens. This is all good. So let's do it again and put 30 sine. And what do we get? Okay. So sine function of 30 degrees equals the Y component over the hypotenuse. So what do you think the hypotenuse is? That's what we measured, 1 miles an hour. It should be making sense. That's all it is. So what was the sine of 30 degrees? One more time. 0.5? Yes. 0.5? Okay, watch this. 0.5. Guys, what's that's telling me is that half, 50% of the 100 miles an hour is happening this way. Now, you may say, well, wait, it's less than 50%, right? Because it's shallow. Let's do the X, and it should be more clear. The adjacent side was the cosine, right? Remember in high school, the cosine was the adjacent side? So in this case, this would be my X component, my cross component. Do 30 cosine, or cosine of 30, and tell me what percentage you get for that one. It's a big number, huh? 86%. So your calculator says 0.86, but what I'm trying to show you is that's a percent. That's a percent. 86% of it is going across. Well, that should make sense because whatever the percent, it has to be going more across than up. And that checks out. 86% of it is going across. That's greater than half of it going up. Now, here's where I'm trying to get paid today. This is where I get the small bucks, to explain to you why those two percentages can be greater than 100. That's the magic of trigonometry, and that's the magic of muscles too. If we were doing our basketball goal analogy, say, we did a displacement and we said, this is 10 feet. What's the shortest distance between 2 points? The straight line, right? In other words, wouldn't it make sense that it would be greater than 10 feet to walk across and then add it to going up? A simple way to put it is, if I were walking at an angle to the corner of the wheel right there, and I counted my steps, 1, 2.5 steps, wouldn't it be greater if I did 1, 2, 3, 4? The x and y will always be greater than the resultant. And you know how I know? Pythagorean theorem. Y'all remember that one? Talk to me about the Pythagorean theorem. What was that about? What did that look like? A squared. You didn't say a plus b is equal to c, right? You had to square those things. That's why. Because a plus b will always be greater than c. The x and the y component will always be greater than the resultant. Because it has to. 1, 2, 3 will always be less than 1.5, 2, 3, 4.5. It's always going to take longer. So that's the magic of trigonometry. There's exponential. It's not linear. Our brains think linear. I get $10 an hour. I work 2 hours, I make 20. I work 4 hours, I get 40. That's how our brains think. But some things in life are curvilinear. It's weird. Meaning, I double my time, but I quadruple my pay. An example. So once you start squaring things, weird things happen. It's not linear, it's exponential. So that's why you can have my y component be half of my resultant, and my x component be darn near 90%. It's almost kind of like cheating math. But that's trigonometry because of the squared part. Because of a squared, b squared, c squared. You got to square it. So how does this make sense for muscles? Guys, we're going to look at muscles, and some of their pull is going to be super obvious. This muscle pulls here. Oh, I can see that moment. I can see that rotational force. But sometimes a muscle may not look like it has a lot. Like what I mean by that is you may look at a muscle and say, well, how in the world, look how steep that muscle is. How in the world can it pull transversely? And I'm like, it has more transverse pull than you think because of trigonometry. Because for only 30% angle, I get the component. Trigonometry. For every small change in angle, I get exponentially more component to a pull. Does that make sense? Because it's exponential. It's not linear. Let's do some more practice. Remember, I'm not ever going to ask you to solve for x and y. I just need you to be able to see it. That's it. Let's pretend I'm pulling. Let's use a force example. I'm pulling with the force of 200 pounds. At an angle, I'm pulling steep. Let's say I'm trying to lift something up, something heavy. I'm pulling at an angle of 80 degrees from the horizon, from positive x. So let's set up what that would look like. This is 90. So 80 would be very steep. Maybe something like that. Maybe a little bit further, but it's not perfect. The meaning, though, is that you know most of that pull is up and not across, right? But here's the magic of trig. Just because it's 80%, 80 degrees doesn't mean it's 80%. That's what I'm trying to get to. Because the angles and the components are exponential. They're not linear. So I know that my x and my y would be perpendicular. There's my y component, there's my x component. This is 80 degrees from the horizon. The opposite side is going to be my y. The adjacent side is going to be my x. just showing you that when you do sine and cosine, all you're doing is saying, hey, what percentage of that overall is here? And what percentage of that overall is there? How much of it is across? How much of it is up? Because X and Y have two different checking accounts, and we have to separate them in order to balance our checkbook. Okay? So, remember, we're doing this in steps. So I'm going to go 80 sine. It's a big percentage. What percentage did you get? 98. So that tells me that the Y component is going to be 98% of the resultant. Guys, that's why when you were doing trig, what happened after you did the sine of the cosine? Didn't you have to cross multiply with it, right? That's all it is. 98% of what? Of 200 pounds. So you'd say 98% times 200, that's actually how much force you're applying in the Y. That's all that means. 98% of what? My resultant. So that means if I'm applying a 200-pound force at an angle of 80 degrees, the Y component is 197, I rounded up, pounds. If you're pulling at an 80-degree angle, dang near all of it is up. See if you could do the X one on your own. Cosine. What's the cosine of 80 degrees? Meaning what percentage of whatever your resultant is going to be in the X. Awesome. 17%. Now your calculator says 0.17, but all that is a percent. 17% of what? Of 200. So 17% times 200, 34.7 pounds. $35 plus 197 is more than 200. That's okay. It should be that way. Going around is always going to be more than going straight there. Campbell, why is this important? I'll give you a few reasons. How many of you work in a clinic? Okay? Athletic training clinic. Heck, wherever you do, you're going to work with people that get hurt. When we do elevation, like someone has a sprained ankle, right? Do we ever prop their leg up like this? That would actually be what's best. But why don't we do that? Because it hurts. Pain is a limiting factor to us trying to heal. But what if I told you you can lessen the pain significantly, but yet not lessen the contribution of gravity significantly? Let's do a simulation. We know gravity's pulling down, right? Let's say our hip is flexed at an angle of 60 degrees from the horizon. What percentage of gravity? We know, we're just going to pretend. Let's say gravity is pulling down mass of the leg. Let's say gravity is pulling down with 50 pounds of force. Just using an arbitrary number based on a plate. How much of that 50 pounds is trying to help bring blood away from that damaged area? This would be 100%, right? This would be all. But at 60 degrees, what you're going to notice is we get more than what we think. So in other words, if it's more comfortable for them, but yet you're still getting a majority of the effects, it's like having your cake and eating it too. So let's do the math. We're going to go 60, and gravity is in the Y, correct? So we're going to go 60 sine Look at that. 86.6% of gravity at a 60-degree angle. You're getting dang near 87% of elevation at only a 60-degree incline. That's trigonometry. That's the magic of exponentials. So it's more comfortable for them, but they're darn near getting 90% of the effects. Does that make sense? In other words, for the extra 40 degrees of uncomfortable motion, you'd only be getting 13% more of gravity. That's trigonometry. It's the relationship between sides and angles, and they are exponentially related, not linearly related. 1 degree of change doesn't equal 1 unit of change. Does that make sense? So all of this stuff walks you down that path of what I just talked about. You need to know these two things, well, more than that, too. Sometimes before you play the game, you need to know the rules. We have two types of vectors. Remember, vectors and scalars. Scalars are just magnitude, but vectors have magnitude and direction. Just like checking accounts have magnitude and direction. You deposited plus, you spent minus. That's all it is. Collinear forces are in the same checking account, meaning that they're in the same direction. X and X, Y and Y. I can do math with them. I can balance my checkbook if they're in the same direction. That's like saying I'm pulling on a rope. If you come pull with me, we can add our two forces together on the rope. But if I'm pulling on a rope and you pull perpendicular to me, you're not helping me and you're not hurting me. You're not in the same direction. Does that make sense? Trig applies to the first one. Got to get our apples and our oranges, so that way we can see how many apples, how many oranges, how many bananas. Concurrent forces, guys. This is the ones that are perpendicular to each other. Meaning, if I jump, if I'm doing a vertical jump or a standing broad jump, and I push off of the ground, I know that the ground is pushing back on me somewhere at an angle like this. In other words, I'm pushing on the ground down and to your right, so the ground must be pushing back on me up and to your left. Does that make sense? If I was in the sand and I jump and I look back, I would leave a crater that's going that way. So therefore, the sand must have been pushing back on me this way. Concurrent forces are two different directional forces, an X and a Y, or an X, Y, or a Z, happening in the same place. In other words, it's a mixture of all the monies. And that's why we have to do trig to separate out what's X's money, what's Y's money, what's Z's money. I'll give you a practical example of this. Let's look at this muscle. We have a muscle F. For those of you watching from home, this is page, what do we have, guys? Page 4 on the trigonometry. Remember, I'm not asking you to solve a bunch of math problems, because in the real world, we're not going to be solving a bunch of math problems, but we have to know how different variables affect other variables. Guys, there are multiples in perfect column, but not all of that pull. The muscles have to literally pull out of the skin for all of it to be X or Y. It's 100 angles. So F is the resultant pull of a certain muscle. This is arbitrary, so it doesn't matter. But some of that pull is up, and some of that pull is down, right? Up forces only influence up motion. Across forces only influence across motion. The up and the across are both happening at the same point, CP. But yet they serve different masters, as Dr. George used to say. Same force. If you have a muscle pulling on a bone, and that bone is attached to a socket, which force, the Y force or the X force, is actually trying to rotate the merry-go-round? And which force is only trying to translate the merry-go-round? Only the F perpendicular is actually trying to rotate. Does that make sense? Well, Campbell, only a component of that motor force is trying to rotate. Does that mean we're wasting the other part? Absolutely not. What's one of the things I keep saying? Muscles are more involved in stability than we give credit. But the parallel component, the force that's parallel to the bone, is helping to keep the joint in socket. Remember me emphasizing that? The stabilizing component versus the rotation. I'll give you this example. You go and grab a couple heavy dumbbells off of the rack, you feel the bicep and your tricep pumping up. You're not trying to do this, but they're contracting to prevent this bone from falling out of here and this bone from falling out of there, and these muscles are contracting these bones. Muscles will at angles, and each component of that resultant serve two different jobs. You have a rotational component, the moment, and you have a stability component. Stabilizing component is literally just trying to take one bone and literally push it into another bone. It's a good idea for stability. And the best part about it is it's not linear, it's curvilinear. So again, sometimes we're going to look at muscles and you're going to say, well, man, that muscle doesn't really have a lot of upward pull. And I'm going to say it has more than you think because of the weirdness of angles and the magic of trigonometry that makes it an in proportional relationship to the angles and the sides. Here's another example. This is on page something. Page 5. So guys, tell me if this makes sense. You have a muscle, but it's pulling at an angle. The perpendicular pull of the long bone is actually what's trying to rotate it. And the parallel component to the long bone is actually trying to keep in something. The shift is trying to stabilize you, and the angular is trying to rotate you. I think that's pretty important. Guys, when you're working a certain muscle, you're not using all of that muscle to rotate. Some of that energy is being used to stabilize it. So a lot of what he's going to do another rep and move on this off the airplane. Make sense? Got it? For some of you, understanding this concept, not just for the test, but angles play a big role in injuries. Certain injuries happen at certain angles because at certain angles, that joint has less stability and more rotary. And at other angles, the joint has less rotary and more stability. You know what I'm talking about. When you're doing curls and you get down here, it's a lot harder because that muscle has more parallel pull than perpendicular pull. Here, almost all that pull is perpendicular to the long bone. Much greater component of moment here than down here. Down here, it's more stability, which you need if you're carrying something heavy. You need more of that component, keeping your ulna in the socket with you. It's also why a lot of elbow dislocations happen when your elbow is flexed, because the stabilizing muscles have more rotary pull than stability pull. It's the trick about you doing this, and I push like this, and it makes your hands fall because they're not lined up. So I'm just asking you to be aware. Does everybody understand the plan? The next week, I'm gonna send out an email, but you're gonna watch videos. Guys, please feel free to contact me. We can FaceTime. I want to clarify. But all of your information, you could work ahead. You could start looking at the lecture on the cervical muscles that you can have on Unit 1. It's up to you. But you have all the information. Go at your own speed, and I'll see you guys when I get back, okay?